Just a minute or two more here. We'll let some more folks come on in. All right. So we got a couple of minutes more. Nice to see everybody as always. Hope everybody's having a fantastic day, staying warm out there. Hopefully your staff is doing good. Hopefully it's a great Wednesday after the holiday here. No one's too buried. But I do know what it's like to have to pick up work after a Monday off, and it almost makes you wonder whether or not you wanted that Monday off. So. All right, we'll do kind of a last check. If anybody is having trouble hearing me or if anything's not working for you, feel free to drop it in the chat and let me know or the Q&A. Either one works. Otherwise, we'll get started here in just a couple more minutes. Cool. Looks like we got a nice mix of people today. Looks like you got some code officials, some designers. Looking forward to this group. Hopefully we get some good discussion going. Hopefully you guys get something useful out of this class today. And we are just about ready to get started here. Okay. All right, guys. Well, thank you so much for joining me for lunch today. My name is Andre Hayen. I'm looking forward to being able to deliver this class with you. I've done this one a couple of times before. I think it's a really important one. I think it's a really effective one to go over something that we all work with every day and every designer works with, every builder works with, every trade works with. But sometimes there is not clarity about exactly how your barriers work in your construction. So we're going to be talking about our air barriers, we're going to be talking about our vapor retarders, and we're going to be talking about our water resistive barriers today and how they work in conjunction with each other, how sometimes they don't work in conjunction with each other, where there's overlap between them, and hopefully just some of the basic building science that helps you understand these as the components that they are and how they fit together as the puzzle pieces that make our exterior walls in our buildings. So I hope it's an enjoyable class today. As always, if you have anything for me here, we're going to have a pretty big group. So today what we're going to be doing is if you have anything, jump into the chat or the Q&A. And if I miss anything, I will review it at the end of class as well. So we'll kind of scroll back through it if you have something that comes up. So you can let me know that way if you want to communicate something kind of through the remainder of the class there. We can jump back to something if you like. But that's going to be kind of the intention today. And we'll go ahead and kind of jump into things and get started. So once again, if you have any trouble, any problems, feel free to drop it in the chat early. I'll try and take a look at that quickly. But otherwise, we're going to get right into the nuts and bolts of how these barriers work and where the puzzle pieces go. So I love this starting off point of looking at the house as a system because a lot of these barriers, they work functionally only in conjunction with other materials, only in the certain placement in their assemblies, and sometimes they won't work together depending on what materials you've put in. And I think this EEBA Builder's Guide statement really kind of speaks to that residential construction is this complex operation and air barriers, vapor retarders, they're not specific, obviously, to residential construction. This is just taking from this particular guide. And we can talk about, the systems that would show up in commercial and in residential, because they're kind of universal in a lot of these circumstances. Materials change, but the concepts don't, right? But talking about construction generally is complex operation of thousands of processes by dozens of industries, bringing together hundreds of components and subsystems into a single house. And that really speaks volumes of this because so many times we're going to look at the different systems that we have available, and we're going to see products that work as both a water resistive barrier and an air barrier, for instance. But you only know that because you do the deep dive through the manufacturer's installation instructions, and you look a little bit further at the products as they're provided to you. And sometimes they'll have some variance in the way that they're installed based on what method or what product you're using for what circumstance. And so this is the kind of stuff that I think really speaks to that, and it really gets us thinking about the building science that is the backing for our energy code. And so let's take a look at the components that we have. This is, in my mind at least, this is a nice map of all of the things that can show up at any given time during our build process. We have our initial framing, right? Wood studs, metal, concrete, and as we're going to talk about, some of those things are porous, some of those things are not, some of those things lead to cavity insulation, some do not, some are paired with other systems and materials, and it's an imperative that we start looking at, okay, what's our fundamental system that's going to be the erection of this building? And then from there, our sheathing and our insulation start to build out that wall cavity. The exterior cladding, I chose this elementary school here as a good representative photo because you have dissimilar materials. And that's always a tricky one with some of these exterior components where they're going to align and how we're going to create those consistencies in the target assemblies that we need to. So that's things like a continuous air barrier, right? How are we going to ensure continuity of that while using dissimilar materials and changing that up? And is enough information being presented to you as a code official, as an inspector, as a builder, in order to navigate that effectively and not miss some sort of material that should be there? We have our drywall or our interior plasters and finishes and things like that. Those are necessary components to building those walls, and those inform us about what's going to be behind it, how it's going to be used effectively, where that air barrier is going to be again. We also have water resistive barriers. Here we have kind of the classic representative of the residential industry. It's usually referred to by name at this point as Tyvek wrap. Now we know that water resistive barriers can be a number of different products that we'll look at today. Things like 15-pound felt, which was used for a good long time. Number of other products out there, and then some assemblies also meet that requirement of water resistive barrier, right? So we're going to look at where all these different requirements come from, and you can see on the right, kind of, we really start to target the essence of class today because everything on the left is sort of the other parts of this wall that are not always going to be there, but pretty much universally always going to be there. But then we get into our three basic types of barriers here. We have water resistive barrier, air barrier, and vapor retarder. And as we discuss these, we're also going to find today that like things like the air barrier and the vapor retarder work kind of like a Venn diagram. They are kind of encapsulating sometimes a bit of the same space. And there's some really good articles and things that I can point you to when it comes to discussing wall assemblies or roof assemblies with double vapor barriers and things like that, where it's like, hey, that goes against conventional knowledge. That's not supposed to work that way. Or we're creating a dew point there and things like that. And so we got to think about the times in which some of these products can do more than one thing. Are they acting in a similar way? And what's that permeability and where's that happening? So that's really going to be the basis of kind of our discussion today. So the first thing I want to point out is that we all have to speak the same language. And if we fail to speak the same language, then we're inviting problems through the build process, right? So water resistive barrier, vapor retarder, and air barrier are often interchanged with each other when we talk about wall construction. They're often swapped out or they're often pointed to mean something different than they are. And now this really gets complicated as we invite our other trades to be parts of this conversation too. Because you get, a designer who sees very clearly maybe how this outlay is supposed to work and what's supposed to happen with this and how this entire wall assembly is supposed to come together. And then as you get other trades working together, who's sealing for what? Who's sealing for your air barrier, right? If that's the case, if your electrician's sealing their penetrations and your plumber's sealing their penetrations and your tinner is sealing theirs, then are we being very clear about what product is being referred to as the air barrier and being identified on the plans as the air barrier? Are we doing that with the vapor retarder? Is it clear where we have spray foam, for instance, or a need to rectify our assembly with other dissimilar materials that might change that permeability factor? So that's really where we're going to talk about kind of getting involved with all of these. So let's go through definitions first, right? Because that's a good jumping off point to have this conversation. And with water resistive barrier, we're talking about a material behind the exterior cladding, i.e., we're back to Tyvek, or we can see here this jumbo text, this weather resistive barrier as it's identified here, and it's meant to resist liquid water intrusion, right? And we know that that's an absolute imperative when it comes to construction generally. We want to control where water runs into a building, where we have moisture, where we have humidity, and we want to be effectively wicking that away from the building, away from our assemblies, and away from the foundation, right? Then we have vapor retarder. And one of the important things that'll point to you if you start digging into this yourself and you grab your code book, if you grab your IRC and you look up vapor retarder, you're going to see the definition includes a concept of class. And we'll talk about that, but it's specific to the permeability. And what that's really trying to, say at a very basic level from a building science standpoint is that we're trying to make sure that water doesn't get in, and when it does get in, it has a place to go that we're telling it to go. And that's the key concept between vapor retarder. And that's also the instances where people sometimes misunderstand that concept and they end up vapor locking walls as they think that, a class one is a better retarder, so that's what we should use. We shouldn't skimp on, what we can use, not realizing that by putting in spray foam in places or other foam plastics or things like that, they're not giving that water a direction. And vapor retarders are about controlling the direction of that water vapor, telling it where to go, almost like a one-way valve, right? You really want to say, hey, we're only letting air in this way, we're only letting moisture in this way, and we're only letting it out this way. And then air barriers. Air barriers is you see one or more materials, and I can almost always guarantee you it's always more than one material, right? If we use thermoply behind a tub, well, we're sealing it in with spray foam. If we use Tyvek, then we are sealing it with tapes and sealants at the joints. It's always more than one material that's creating a continuous barrier to restrict the passage of air through the building thermal envelope assemblies. And we're going to talk about that in more depth. But what I really want to highlight there is the one or more things, because that to me tells you that it's a system of materials. Sometimes they're similar, sometimes you're using materials that don't necessarily tell you to use the materials in that particular fashion. But we know that we have to create that continuous seal to restrict airflow. And so this is about knowing that how. Once you really identify that how, we can spend time on the why it's applied and how it's going to work in that particular circumstance. All of these definitions were pulled from the 2021 version of the IECC and IRC respectively. However, those definitions really have not changed. So if you're on the 18, I would tell you these are identical to what you've experienced before, by the way. So just want to make that clear to everyone. So, with our insulation and our air barriers, one of the most important things to know is that they create the thermal envelope. You're seeing more and more code sections clearly tell you that it's not only where there's insulation that's going to break up things like having a mechanical room inside of your house, right? And you want to isolate that thermally, or your ducting, right? To make sure that it's properly buried to be fully within the thermal envelope in those places that abut, outside or an unconditioned space, right? It's telling you that you need the continuity of both your insulation and your air barrier in those places. That really does produce our thermal envelope. Vapor retarder and insulation work together. And again, this goes back to that concept of permeability. So a couple of these really work together in a unison-like fashion. And if you're thinking about one, you kind of can't think about the other without understanding. You notice water resistive barrier is kind of out on its own. And to a degree, that's kind of true. We want to make sure that it's kind of clear to everybody that these are the ones that are really trying to work together within that wall cavity to make it clear where that moisture can go, where that air is getting washed, and that's being limited down as much as possible. Whereas your water resistive barrier is a much older requirement that's been around a lot longer and really focuses in on wicking that moisture away from the wall assembly, away from the foundation, telling it where to go. So where do these requirements come from, right? And right here, I'm going to highlight for you for the 18s and the 21s, right? The water resistant barrier is coming right out of the IRC, and we're going to talk about Chapter 7. Your air barrier is going to be different. It's going to come out of the IECC because it's part of that thermal envelope requirement. And then your vapor retarder, because it kind of crosses both lines there, right? It is about directing moisture and mildew buildup and those sorts of things from the assembly, and that's why it's imperative on the IRC side to really understand, especially when designing things like your attic spaces and some of your wall assemblies, because your wall assemblies are innately more and more complicated. And then it also ties directly with the IECC because it's tied to your insulation. So this is the start of where we're going to point out, hey, not only are the definitions of these particular things different, but where they come from and what you cite is fundamentally different in a lot of these places. And understanding that and pointing that out to folks really helps set those expectations clearly. So let's start with our water resistive barrier and let's start with sort of the exterior of the building as a whole. Now, water does damage, right? When water gets into assemblies, the first thing that starts to happen potentially is mildew or rot, and you're starting to degrade those building materials earlier than you are supposed to. You also can suffer from a freeze-thaw effect if you're in the right climates, like here in Colorado, where it's, absolutely freezing outside these last couple of days. You know full well that if you have, water intrusion, whether that's from a burst pipe or whether that's because something is getting in past that water resistant barrier, as it freezes, it expands. As it expands, it creates more of an entry point for more water, more mildew, right? And it becomes a feedback loop. At the same time, our air barriers are sort of doing similar things. That's why I say that they have this overlap like a Venn diagram, but functionally they're designed to compartmentalize buildings, and that's tied in with that thermal envelope. But you can also see that this is some of the ways that we promote safe and healthy buildings through a life safety component, right? Air barriers help prevent the transmission of hot gases and smoke from one compartment to another within a building, like this multifamily building suffering this fire right here. We can also see that, different fumes or gases that might typically be present in things like a residential building. So the way that we separate our garage space from the rest of a building is imperative because it's built on an air barrier fundamentally. Even before we're worried about the concept of retaining that heat and that energy efficiency with our insulation, we're really concerned about compartmentalizing that area for the fear of carbon monoxide poisoning, right? And then, of course, we have our thermostat there, and the reason we have that there is because, the way that we heat our house and the way that we make sure that we mitigate some of our humidity is through our mechanical equipment as well. So we're using all of these things together as a system, like that EEBA slide that we had earlier kind of pointed to, that we're thinking about all of these things together. So moisture is our number one concern, right? Moisture is truly the biggest issue that we worry about, and that's why water-resistant barriers have been a requirement for so long. We can see the mildew and the rot going on here, and probably the adverse effects that are happening on that system. The insulation likely is shrunk up and carrying substantial debris in that material that's going to prevent it from being able to work effectively. Freeze thaw in this might be causing the sheathing to open up even more, allowing more air and water intrusion, and it starts to become a vicious cycle, a vicious feedback loop, right? So we get that reduced R value, we get mold and mildew, we get deterioration and rot pretty quickly, right? Our moisture sources can be a number of different things. It can be our bulk water, our vapor diffusion, and air movement. We're going to talk about some of those places that those things can really come from here. So let's talk about our phases of water because we've mentioned more than once that we have vapors, we have freezing, therefore solids, we also have liquid intrusion, right? Liquid intrusion is the one that I think we're most worried about on the exterior of buildings because we know that it wants to follow the path of gravity and the path of least resistance. So if it's able to find an opening into a building, these are our roof leaks, these are things like our ice damming at our eaves that then eventually creates some capillary effect where that starts to work its way into things like our softening and really into the rest of our systems there. And then, of course, we have vapor diffusion as well, right? So these are sort of the concerns that we have, and our building is subject to all three of these all the time, right? Water vapor through humidity, but can be from ambient sources. That can also be from cooking appliances. That can be from a number of different things. Ice, obviously, in Colorado, major concern, and then water intrusion generally for everyone is a major concern. So focusing on controlling the water, our first line of defense is to keep the water from entering the building in the first place. The second thing is to make sure that it can't accumulate. So when we think about our water resistive barrier, right, that's behind our exterior cladding, if water gets past the exterior cladding, which the cladding itself is supposed to try to prevent to some reasonable degree, then it's supposed to wick that water away. So it's preventing accumulation. It's letting it basically roll down the wall and exit away from the building on a drainage plane. That's that removal of moisture. So that's really what we're predicated on with this, right? So how do we do that, right? Well, we prevent surfaces from getting wet and getting any intrusion into the interior. And then if they do get wet, our focus is on making sure that they have the opportunity to dry out. That's really the focus here. And I do want to cite that this particular slide and kind of the contents of it does come from Building Science Corporation's article there. It's cited at the bottom left from Joe Stiebrick. He's a phenomenal resource on this topic. And if you want to get into especially more complex systems, he's one that I could really point to say that you have some really great literature out there and some free PDFs on his website. So if you haven't checked him out, he usually teaches regularly too. I don't know if he's teaching at the Colorado Ed Institute this year, but a great resource on this topic who's spent a lot of time doing it, and I will cite him more than once today with some of the stuff that we'll be covering. So, in limiting the damage here, sorry about that, from limiting the damage here, our water intrusion really starts at our water resistive barrier, right? We're trying to keep that from happening. Our vapor retarder is trying to give that water a direction. Where we know that we are going to get some moisture into the assembly, we want to make sure that we are directing it out effectively. And our air barrier, whether it's on the interior or the exterior, like this picture shows, is helping ensure number one, that our thermal envelope is continuous and it's able to functionally do its job, and we're able to get the energy savings that we have designed out of this thermal envelope that we spent so much time building and effectively creating. While simultaneously compartmentalizing the building from other places where we might get intrusion of smoke, intrusion of moisture and humidity as well. So this is where that overlap really does exist, but it doesn't change the fact that we have three separate products performing three different services to this building. There are instances where one product can do more than one, but we have to make sure that we're installing it accordingly and doing its job correctly. So our first code here when we talk about this, water resistive barriers, another old hat one that I think is a really good example of trying to understand these assemblies is our roofing underlayment. But, we look at water and we look at water intrusion and we see instances beyond these where it wants to make its way into building. These are capillary breaks. So anyone who has worked in concrete, for instance, knows that, concrete can act as a wick. It will draw moisture through. It is permeable in that sense, and water does want to pass through it. That's why we moved to doing things like treated lumber for our sole plates, right? And we started using things like sill seal for a capillary break on some of those, and that's why we get our designs for our foundations the way that we do as well. When we look at our footing and stem wall, which sometimes will incorporate a capillary break, and of course our waterproofing and damp proofing, which we can definitely see in some of those humid places that we worry about, like crawl spaces, where that difference is really profound, really significant. So for phases of water, obviously we don't want solid water in our assemblies at all. We try to not let it become a liquid either, but we know that that's part of worrying about where we put certain parts of this assembly, our vapor barriers, right, and working with our air barriers. We want to make sure we're not creating interior dew points in the building where that water wants to consolidate into moisture and then move from that liquid state into a place where it can possibly freeze. And we want to make sure that we're draining it away. Now, we will talk about insulation and air barriers with significantly more depth here. You can see from this example on the left-hand side, we've got a significant amount of ice damming here, and this is why we've moved to using things like ice and water shield or ice and water barrier, right? Sometimes you'll hear it referred to that way. I think that's more of the general term than the sort of like product name, ice and water shield. But that being said, that's really recognizing the fact that we have a high propensity for intrusion in this particular place. That, the framing there is difficult to maintain, getting a consistent, tight seal, and that's where water wants to accumulate because of the freeze-thaw process, and it loves to just worm its way in there through the capillary effect and really start to work up some of that roofing material. So With the water resistive barrier, the first thing we're really going to point to is 703.1.1. This is our first code section that says, hey, you will provide something here. We get a couple of exceptions here that let you know that you have a testing requirement that you can design to, and certain flashing requirements as well. But this is the first place that we really get a look at it for saying, hey, you will provide a water resistant barrier behind our exterior cladding. And that's going to make it very clear about what these next steps are going to be. Bulk water wants to find the path of least resistance, and so this is what we've been talking about when we're talking about the worst conditions for intrusion. But we also recognize that it generally follows gravity. This is that wicking concept that I mentioned earlier, that you can see that moisture in these blue lines being targeted up through the building and now coming into places where it might be damaging that insulation or not allowing it to perform to its best. We can also see in our concrete designs here that our dam-proofing membrane is acting as a capillary break, so that way we're not wicking that moisture from the footer into the rest of the stem wall here, and other places where it can be drawn upward and not necessarily follow the path of gravity for it. 703.2 really starts to give us the rest of what that water resistant barrier is. So not only do we have to have it, but here are the requirements for it. And here we see that 15-pound felt as an option, other materials installed in accordance with manufacturer's installation instructions. And that one's an imperative, right? There's a number of exterior products out there that we're very much used to. Zip system, for instance. Zip system is a great system as long as it's taped properly, and that tape needs to be rolled down with their rollers. I mean, it has an installation methodology to it that is more than simply, putting it up, nailing it off, and sealing the joints. It's got specifics, especially when it comes to penetrations and things like that. So when we sign on to use that material for our water resistive barrier, we're using it for all parts of our water resistive barrier there. And so we have to make sure that we're following that requirement to the letter in all of the installation that's required. So here we have a couple of examples. Out here we have stucco, or it could be adhered masonry veneer. We have a water resistive barrier there. Now this is an important one because our Portland and stucco manual is basically telling you here that you really have two papers that you use for this, right? One being a bond break and then one being your water resistive barrier. And that's been a common method for a long time with these stucco systems. But it's one that if you haven't had a whole lot of experience with those, you would think you're putting up almost a redundant amount of building paper, and you'd be wondering why. So your Portland and stucco manual is a great one. Portland plaster and stucco manual is a great resource to be able to look at this with a little bit more depth. But here's a perfect example of providing that water resistive barrier, knowing that there's a propensity for intrusion with this system. And so we're leaving that drainage plane with a flashing to take this away from the foundation. And it's meeting the rest of the kind of the needs of that wall assembly. But it is a great one to bring up that stucco and masonry veneer are treated slightly differently in that. So here we go. Here's Tyvek on a multifamily building, right? And right here we can see the tape job that they're doing at every window, at every seal there, at every seam, right? And there's specific lapping requirements for those seams as well. And we should have that ultimately clearly stated on our building plans for what material we're going to be using, right? So we have an air and water resistive barrier that's stated here. Well, air and water resistive barrier points me as an inspector, as a plan reviewer, to have to look at a couple of things, right? Is the selected product on the outside there? First of all, I don't know what it is if this is the only plan that I've gotten, right? It just says air and water resistive barrier. Do I know of products that can do that? Yes, Tyvek is definitely one of them. If I'm out there as the inspector on this, that means that I have separate installation requirements. And if you go and visit their manual, you will see that for penetrations, they'll have additional taping requirements. For windows, anything that penetrates that membrane, they'll have separate installation manual requirements for it. I think the laps are the same last I checked for this. I don't think they changed those. I think there was a time that they did. But ultimately, this is one of those moments where are we getting enough at plan review? Are we getting enough at inspection to say that we know what material is going to be used and how it's going to be used, and we're making sure that we're meeting those requirements as a manufacturer. So let's move on to vapor. Vapor is an interesting component in this, right? Because vapor is essentially our humidity, and we like things as human beings. We like things relatively humid, right? Your manual JD&S basically requires you to design your system at 30 to 50% ambient humidity, at 70 to 75 degrees. So that is sort of our basis case for what humans sort of deign to be comfortable or believe to be, the environment that they want to live in, and especially in a dry climate here in Colorado. I know plenty of friends that have humidifiers running nonstop. I think a lot of folks, especially in the winter months, definitely see a need for that. And that water is going to move around in your building. So are we telling it what it needs to know? So what are some of the sources of moisture in that building? Well, we already talked about cooking appliances, for sure. Showers, right? Showers are definitely notorious for this, right? We're lucky to be in as dry of a climate as we are because that doesn't usually lead to mold and mildew, but certainly I've ran into my fair share of circumstances here in Colorado with the wrong assembly, and it really can if it's not vented properly and we're not getting that adequate air supply into those rooms. People. People create an ambient amount of humidity. There's no getting around it. We are mostly water, and as such, we contribute to a building as mostly water. Plants are another big one, right? And that's not just like the greenhouse or the three season sunroom that has a ton of plants in it, but generally, I would say, and it's kind of weird to mention, but especially with people working from home more and the work from home revolution, I'd say a lot more people have more houseplants in them because they, this is their office space. They want it to feel a little bit more bright. A lot of people took up a lot of like cooking habits during COVID, and so now they've got, indoor herb gardens, or those kind of like PVC plant stand things that you can grow a million vegetables in and all the rest. A lot of people are into, horticulture within their buildings at this point. And that makes a significant difference in the amount of ambient moisture that you can expect in a building. And of course, intentionally humidifying spaces like humidifiers there. So all of these are contributing to a vast amount of moisture within the building. And how are we responding to it in kind? So vapor diffusion follows the same rules of thermodynamics and the same rules of physics as everything else. When air is significantly humid, it wants to normalize with non-humid air, right? It's the same thing as heat wanting to move to cold. All physics, basically, everything wants to normalize, until it's all ambiently the same. That is what everything wants to do over a long enough timeline. So you can see here when there's a lot of humidity, let's say this is the inside of the building on the left, and then on the right, this is a diffusion process where this is passing through an assembly, and this is what's on the outside, right? Well, naturally, this moisture, just by physics, wants to penetrate this assembly and move into a place where those molecules have basically room to relax. And so they are going to get to a place where they can normalize. And this is kind of the ambient sort of pressures in physics that are pushing that moisture through other materials, right? It's a function of temperature and relative humidity, and it's also a function of pressure itself. And we'll kind of get into that as we look at the metrics for things like permeability. So this again is at this point, I'd say kind of like an industry famous sort of experiment by Mr. Joe Stiebrick, who, if my understanding is correct from what he taught, it's really interesting. He basically created the same assembly at his house and tested it to see how much water diffusion would occur for a 4x8 sheet of chipboard at a same, a standardized temperature and humidity. So you have 70 degrees and 40% relative humidity. Um, for just a sheet of chipboard, this is how much water is going to end up flowing through that over its lifetime. It's 400 milliliters over the course of a year. Now, if I put a 1 inch by 1 inch hole, right, in that sheet, and now we're able to clearly leak that air through and diffuse it, now look at how much water is coming through that. It's almost absurd that it's 60 times as much that is actually passing through that assembly. And I think that this speaks volumes of not only the build tight, ventilate right sort of sort of strategy that we've taken up for the longest time. But really just how much these systems passively are fighting for creating those those controllable environments and those relative ambient temperatures and humidities. And we think about it, who's going to walk around their house and punch a 1 inch hole in it and allow this to happen? But you think about all of your escutcheon plates for your sprinkler systems. You think about poorly cut outlet cuts, right? Those covers, I'm sure, I mean, they're plastic. I would venture to guess they're impermeable, but they don't have a perfect seal by any means. They're certainly not usually meant to, especially in places like residential construction. They don't have a gasket or anything behind them. So they're not getting a perfect seal. And you think about an inch is not that much space in a 4 by 8 sheet. And the amount of times that this can occur over a house can really start to lead to a significant amount of water intrusion. So this brings us to our vapor retarder. And this really gets to the heart of where we're starting to try and control that water, knowing full well that it's going to get into the assembly. Now, for those that had to join a few minutes behind, I kind of did mention a little bit earlier. And I do see that there are a couple of folks in the chat, and I will definitely get to those at the end. We'll go through our questions, no problem. But for the folks that joined us a little bit late there, we're kind of talking about these puzzle pieces and the way they're presented in the core code in sort of an idyllic form. I'd strongly recommend if you've been running into circumstances where you're getting some really complex assemblies in the high country, you're worried about vapor locking roofs or wall systems, you're getting more exterior insulation being mixed with more stringent, like class 1 vapor retarding systems, and whether or not that's at all possible. Again, I'd point you back to a couple of those Joe Stiebrick articles, and if you want to find me in the chat or email me after, I'm happy to shoot you some links of them because I think he does a really good job on some double assemblies and really explaining how those have worked historically, despite kind of violating the rules, so to speak, on some of this. So we'll be talking in sort of idyllic circumstances, but the science is still there, the science is still valid. So when we talk about vapor retarders, we talked about the classification, and the classification is a function of permeability. And permeability, as we understand it, is how much vapor material can allow to transmit over time. So when we talk about transmit, I really want to draw your attention to this last sentence down here that says perms are measured in grains of water vapor per hour, per square foot, per inch of mercury. And so what that's really telling us is we're going to standardize the space, right, per square foot. We're going to standardize the timeline, and we're going to standardize a pressure because with enough pressure, you can force molecules through other materials, right? So by looking at all of those things and trying to standardize them, then you can look at what that ASTM E9605 is really testing for, which is that transmission component because you're standardizing the rest of it. So that's why it's expressed that way. And it seems maybe overly scientific, but that's just sort of what they're trying to get to with that. And so for this right here, I pulled a nice list of some of the typical perm ratings for some of these things. But I would, kind of venture to the rest of the class, what exactly is a perm, right? And it's the amount of grains of water, and that can pass through, like we just said, a certain amount of square footage under a certain pressure and all the rest. Well, how much is a grain of water? Like, what does that mean exactly? And for some of the folks that are on this that are into, some really high precision hobbies like, bullet reloading or things like that, they're used to working in extremely precise measurements. And I know we have some scientists and some folks with lab experience on the call as well. So, for those of us that are uninitiated, I did a little bit of looking on this, and here's the best sort of analogy that I've been able to find online is take a penny and cut it into 2.5 billion equal pieces. And that's billion with a B, 2.5 billion. And now count up 58 of them. And that is a grain of water. So when we talk about perm ratings, when we talk about a grain of water, we're talking about an almost infinitesimally small amount of water, but a discernible amount of water. And as Joe showed with his, previous example, that sheet of drywall is permeable as is, right? And it wasn't painted, it wasn't anything like that. So that's just that raw drywall and how much moisture is passing through it. And then we can see that we have a number of other things like latex paint and things like that that are contributing to giving us the perm rating that we're after. But this is where aligning with our insulation is really important because we have air impermeable insulations. Not all are, and we're going to talk about that a little bit. So here we have our classifications right out of the IRC. So our very low permeability vapor retarders, that's our unperforated aluminum foil, our visqueen, that's going to be that zero point 0.1 perms or less. So that's saying that zero point 0.1 of that 57 2.5 billionths of a penny, um, that's how much is getting through there. That's extremely low permeability, and that's the level of testing that we're actually talking about with that, which I find to be just absolutely incredible, right? And then class one is 0.0121. So it's that intermediary category there. That can be things like craft facing on bats, right? And then we get to our medium permeability vapor retarders, and that can be 1 to 10 perms. That can be things like our latex paint and things like that. So hopefully that sort of relates now when you start to talk about this and you start to explain why to somebody, hey, you can't use all of that closed cell spray foam in that wall cavity and then cover it with visqueen, and they say, why? It's better. I'm using a better thing, a low permeability. Aren't I doing a good job? And you get to explain to them, no, what you have done is you have created basically like a steam box, right? Where any moisture that was ever in that system will live there and just continue to condense and continue to rot in that space because you're not telling that water where to go and why. You're not doing it with intentionality. You're closing it off because you think you're using the best products on the market without regard for why they tie together and how they tie together. So here we get some of that guidance here, right, for vapor retarders. And we can see class 1 and class 2 vapor retarders are required for certain climate zones, with exceptions. And we talk about basement walls. Why would that be? Well, because basements are notoriously more humid. We know that concrete wicks moisture in, right? The below grade portion of any wall, again, we're contributing to that conversation about where's grade, where's humidity, where's our dew point, right? Where are the things happening that are really going to matter for us? And where moisture freezing will not damage the materials. So that can be, certain materials that we don't have to worry about because they're impervious, right? Class 3 vapor retarders can be permitted in any of these conditions. Now we're starting to take a look at that and really scrutinize why would class 3 be so ubiquitously allowed to be used? Well, it's, considered things like latex paint. Then we use a lot of latex paints in buildings. It's also, depending on the construction and making sure that we're not also using a vapor retarder that we shouldn't be using for that particular climate zone, we are telling that water where to go in that process of that wall assembly. So here we have it broken down for us by climate zone here, and I have 4, 5, 6, 7, and 8, just because this class is specific to Colorado, where you can take a look at for your class 3 vapor retarders where permitted, right? We also get some specifications here for exactly what the code is pointing to for our sheet polyethylene, craft facing, etc. So now we're going to jump over to air barriers. And like I said, I promise I will leave time at the end here to be able to hit questions. But I do want to make sure we make it through the remainder of the material because we got about 20 minutes left here. So how long have air barriers been required by code? Any guesses out there? Any ideas how long air barriers have been in the code? We've got generations of this dating back to 2000 now, as you can see on the screen. Any ideas how long ago? Okay, I'm not seeing any guesses, but I hope everybody's enjoying a sandwich at lunch or something. So since 2000, since the very first iteration of the IECC, oh, I got somebody in there. 2003, yeah. Just before that, Brian, just before there, the very first iteration of the IECC had a requirement for air barriers in this code. And it's because they're so endemic to the process of building a good thermal envelope. And so we're going to take a look as to why that is and what role they're playing in this assembly as well. And the first thing I want to highlight is that air leakage is a major concern when we're talking about energy efficiency. I know that there's a lot of desire out there. I watched a great, I hope some of you were able to join it as well. The Noresco team put on a great class this morning for heat pumps and where they're used best, how they can be efficient, and I think it's wonderful that there are so many bits and pieces of technology that are really trying to push the envelope on efficiency. And yet, at the end of the day, I also still come back to without a good thermal envelope, it can't do its job as a heat pump and so many of these other things that we take for granted, even as minuscule as equipment sizing, does not work. And that is partially due to air leakage contributions. Air leakage can account for 25 to 40% of the energy used in heating and cooling a typical residence. That's an insane amount. My grandparents always said, like, don't light your money on fire, understand the value of a dollar. And this is about as close as you can get to that, right? That 25% of your heating bill is just your warmed air that you spent money on already leaving the house because it's not air sealed enough. And there's a great DOE study that really speaks to this at length that goes over a number of states. I believe they studied 8 states in this, and about a third of homes did not meet the leakage requirements. In fact, oh yeah, that's what that says in that next sentence. And yeah, you can see it's $1 million based on statewide energy costs. When you think about like the grant funding that's out there for trying to improve residences, this is a totally targetable place that can really make major improvements. This is one of our best strategies for being able to passively increase the heating efficiency and cooling efficiency of a house without having to have the major expenditures on things like equipment or replacing systems. Can a home be too airtight, though? Brian, you raise a really good question. We definitely know that there are instances of sick building syndrome, right? And things that we have to worry about with that. I would also point to the fact that, like, in order to hit that tight of a building, it's way beyond the prescriptive confines of what we worry about with code. So, FIAS, for instance, that's the Passive House Institute of the United States, has a threshold for its air leakage at zero point 0.3 air changes per hour. And as you probably know, in the IECC, that's 3 air changes per hour. So that's 10 times as strict. And you don't hear about, instances of sick building syndrome necessarily with a FIAS house by definition, you know. And so I think a lot of that comes from the fact that they're also using HRVs and ERVs for bringing in the necessary amount of mechanical ventilation for that home and things like that. And look, I am also one of the first people to usually point out that very common sense argument that look, you build a very tight home, a kid leaves a window open, and you lost any advantages that you have, and that is true. Like there's no getting around it. I attended college at CU right up in Boulder, and I lived in this apartment building with this old lady, and there was like no air sealing between these units, and you could smell what she was cooking, and sometimes it was good, sometimes it wasn't. And she also kept that house at like 1,000 degrees. And so my unit, just over in the same like converted house, was like 1,000 degrees all the time. So I like slept with the window open midwinter. Like these are the kind of things that compartmentalization can help with that. And so by adding that air tightness, you can make those improvements that I think are common sense. But you are right. There is a certain point of not only can it be too tight that you have to worry about getting sick, there's also a tightness factor that is diminishing marginal return, where you're spending hundreds and hundreds more dollars on more sealants and trying so hard to wrap this building up. And yet at the same time, you're only making a marginal improvement, if any. So I think for more than one reason, there is sort of like a too tight on the bell curve point. But we're certainly not anywhere near it when we talk about prescriptive code. So I really do love this diagram here because it points out, especially if you're training new inspectors or you're trying to create a handout for a homeowner to understand what it is that you're trying to attack with air leakage. This is a great example to just point out to you, hey, these are all the places you're losing money in because it's not sealed. And when you point it to them like that, man, do they tend to get it at that circumstance. You know, they really start to see the value in spending the extra time and understanding a little bit of air sealing. So I would just kind of point to this and say this is a great resource out there for you, and it's a great one to inform today's conversation. So again, we already talked about this one or more materials, and I love this photograph of the thermal ply behind the tub because we really do have two materials being used that no one expressly really said at first, hey, this is the right way to go about doing this, but we figured out pretty quickly this is the necessary amount of air sealing in order to make sure that we're not leaking the air from, that even the warmth you put in that tub, right? You draw a bath of hot water. Hot water wants to normalize to being cold, and so it's passing that heat through that wall if it's not sealed up properly with an air barrier. So I think it's just a great example of that definition as a whole. So, like I was saying, most insulation is not an air barrier, right? Most insulation is air permeable. Its job is to reduce thermal conduction. It does not resist airflow. That's the job of the air barrier. The air barrier is meant to basically lock that away, lock that in place, and create a dead pocket of air now. And that's why its continuity is just so dang important in this conversation. So, what's the biggest insulation myth? that insulation stops the movement of air. No, it doesn't. Insulation does not stop airflow. Insulation likes to capture air, but that's it. It does not stop it. It can't resist wind washing. A great example of this is these two jackets, right? If this was October, the jacket on the left would be totally usable for plenty of folks, right? The insulation's trapping some air. It's a little brisk out, but it's like pumpkin spice season. You're going to be fine. You can go for a walk out at the park. You can go to Wash Park in that jacket and you would be perfectly fine early October, right? Be happy as a clam. But you get to this month and you pull out the winter parka. You pull out that North Face over there on the right. And the reason is because that shell on the outside is stopping that scrubbing of air and preventing that from taking away all of the warmth that your body has created. And you notice I really think it speaks to a number of the reasons that a number of the things that we're looking for in a building. It's durable, right? Because we get a hole in that jacket, if you're going skiing, you get a tear, in the arm or something. Lord knows I've had that happen, and then you're freezing in that particular section. All that hot air that is being created is leaking out. It also speaks well to the concept of the dew point. Who has gone skiing and gotten sweaty in their jacket, and now you're freezing because that air or that moisture is now turning to sweat, and now you're getting, like, not to be too gross, but you're just getting to that point where it's like, no, my sweat is now making me freezing cold now. And now you have to open up that jacket and intentionally let all that air out, let all that heat out and that humidity, because now it's just condensing and you're getting colder and colder instead of the jacket doing its job. So this is a really good, like, fundamental metaphor to use for a lot of folks in this discussion. But the real focus here is about creating control. An air barrier is going to be continuous. That's why she's got the sleeves that latch down. She's got her hands in her pockets. She's got the hood that can button up as completely as you can get, right? It's going to be impermeable to airflow. It's not going to let that air out and escape, and it's going to be durable. So that's really what we're talking about with those. And to highlight again, those air barriers are systems. Those systems are totally about control, controlling airflow. And again, just like our vapor barrier is about controlling moisture. In this case, we're talking about controlling airflow. So this is, in my mind, a really good reminder of why it's so pertinent to this conversation, because our air barrier stops the scrubbing of air, but it also reduces pollutants from entering the building. Um, my first house that I bought was a 1950s brick ranch, and if there was a wildfire in Colorado, I could smell it when I woke up. Didn't matter where it was, I could definitely smell it. And it's because that smoke was getting in. As I worked to try and air seal that house and make those improvements, that dissipated over time. But that's pollutants. That's, exacerbating asthma and things like that. That's important to our constituents. That's important to our builders, because they don't want those callbacks either, saying, "Hey, every time it's crummy outside and there's some wildfire, it smells like a campfire in here." They don't want to be called back for that either. So it's better for everybody if we can address that from happening. But that also means then, if that smell of smoke can get in, actual smoke can get in, and if actual smoke can get in, that's that compartmentalization between units. So I've shown this picture a lot. A lot of people think this is mold or mildew. What this is dust. This is dust particles that have just kind of fed into this insulation. And you can see where it's gotten more spindly in those places, and it's certainly not as pink and fluffy as it once was when it was put in. And that means it's not doing its job very well. And if that air can carry dirt and dust, it certainly can carry moisture and mildew as well. So those things can certainly get in there. But this is what we're fighting at a very basic level, right? We're preventing this from happening and trying to keep these materials as durable as they can be for the lifetime of their installation. So what I want to highlight for you here is that your air sealing details are identified in 103.2 in your plan review checklist, so to speak. And that's what I call this section. This is the "did I even submit enough to do a review" sort of checklist. And air sealing details tells me that we are talking about details expressly. And we get a nice chart of them in 402.4.1.1, where we get a breakdown of our ceiling, our walls, our attic, our penetrations, our narrow cavities, our recessed lighting, right? Each iteration of the code has added to this chart in some way or another, and each of these should be provided as a detail in your plan in order to be able to say, okay, I know what the air barrier is in this circumstance, and to make it clear to everyone who now has to go and seal all those penetrations. You know, I made this slide kind of laughing when I threw in the cable guy thing because they to me were always the most notorious ones for taking like a hammer to, make a hole for a quarter-inch cable or using a 4-inch hole saw for a 1/2 inch data cable or something like that. And so I had a guy that ran like 6 holes through every draft stop in a multifamily building on me doing exactly that right before final, and the super was just coming unglued over him. But I mean, these are all the examples of all the places where we intentionally put holes in an otherwise air-sealed, airtight box that we've been trying to make. So we spend so much time trying to build a comprehensive thermal envelope. And then we have to, as human beings, we want doors, we want windows, we want plumbing, we want fire suppression systems, we want heating equipment, we want data cable and the ability to, have our TVs and our routers and things like that. And we want electricity. And so those are all cause and reasons for us to go ahead and start putting holes in the very thing that we started to try to build to keep that from happening, right? And so this is why this is enumerated in the code, not just as being, hey, you need to have an air barrier. You need to tell me where it is, and you need to provide details like the one in the top left there. Because you're going to tell me how we're going to seal this up so we can make it demonstrable to everyone who has to work on this building. Make it nice and clear what the expectation is for sealing. It's a job aid for everybody. Plans examiners, builders, and inspectors all benefit from forcing the issue of saying, hey, that 402.4.1.1, you're going to treat it like a checklist. You're going to give me a detail for everything there that's pertinent to your job. So, kind of a fun little quiz here. I love this one of where does the air barrier have to be located? Because we've talked about it on the interior, on the exterior, and the answer is it can be anywhere in the wall system as long as it's continuous. And so it's actually not in the residential IECC, it's in the commercial. You can go to the relevant section for air barriers there, and there is a list of materials that are available to you. But not only that, it also gives you things that are tested in accordance with the ability to be able to be used as an air barrier, right? That's why I have things here like a zip system. But OSB sheathing actually is a viable option right out of the code. ICF and CMU are actually in the assemblies section in the commercial. And that's where you find those, where you find that the permeability of a certain system, full grout cell, and yada, 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 is told to you for all the things that you need to do. And it says, okay, if you do that, then you have a system that functions as an air barrier there. We also know our foams, open cell and closed cell spray foam, have different permeability based on density and based on installation depth, right? Um, we also have interiors like drywall, gypsum plaster, and cement board. So any one of those things can be an air barrier, and that's why it is so important to get that clarity from the designer of what they want the air barrier to be. Because it can be any one of these things, and when you run into dissimilar materials on a building, sometimes you have to switch. Sometimes it was, hey, we're using a CMU wall on this section, that's great. And then when we stop here and we move to a hardy board, now we have to think about which system we want to use for this. So do we want it to be the Tyvek or do we want it to be the chipboard on the interior? Great. That's the kind of thing that needs to be spelled out and why we need to think about it in the holistically, how we're using the building itself and what materials we're pairing with it. So here's that example Atom assemblies. So this is C402.5.1.4, where you get the pointers to tell you that your joints have to be sealed and what your requirements are for these installs. Your masonry walls shall be units of 4 inches or more, right? But this does tell you that these assemblies meet the requirements of an air barrier. So here we're going to kind of come more towards the end and wrap things up here. And we're looking at water resistive barriers. We're keeping water from entering the house and adding a path of travel to take it away from the foundation, take it away from the building at every chance we get. Air barriers are about preserving our insulation, making sure that our thermal envelope is working effectively. And our vapor retarders are about keeping moisture from, our inhabitants, from those interior systems that we were talking about, from entering that wall system. And when they do, giving it a clear path out. That's the whole system. That's all three pieces now trying to work together in this system as one. So let's take a look at some plans, right? I really like to finish with some real world examples. And here we can see we have a garage vapor barrier, we have an interior vapor barrier. First question I point to, should we have two vapor barriers on a wall? The answer to that should be a no, right? Warm wall usually indicates where that vapor barrier is going to go. And so we have it on both sides of this, the garage and the interior. Now that could be a misnomer where that was supposed to be a an air barrier on the exterior there, right? That would make sense at the garage wall. But this is the exact sort of scenario where it's undefined and unclear and therefore can cause a problem. And it might be unclear to the tradesmen that have to run penetrations through that. It might be unclear for the guy who's going to buy the materials, or the the architect who she's doing the purchase orders for this and putting together the takeoffs for what the materials are supposed to be, right? And working with that design or with that builder on that. It could be any number of roles in this that are affected by the scenario. Now, what do you think here? And I will tell you there's spray foam in the cavity behind this. And now you can see that we have a framed out box for what looks like maybe a fireplace setup here. This looks like a nice living room. And we are about to vapor lock this wall. That's what we're about to do with this, right? That visqueen being used as a class 1 in conjunction with a non-permeable insulation is exactly the concern that we want to point to and say this is what's avoidable. This is what we don't have to do. But this is also an easy mistake to be made. Here's another great one where we have an example here of closed cell spray foam in this wall cavity. We have 2 inches of it. Now, 2 inches of closed cell, that's more than 1.5. That meets that requirement for air impermeability. And now we have class 1 or class 2 vapor retardant. Well, which one? I mean, that's a significant difference there. One's craft facing and one is potentially a problem, right? Potentially a hazard. And this is exactly why that matters. Now, I promised you, sort of a brief discussion on Joe Stiebrick's thing about that. And basically, I'll sum it up as best as I can, as quickly as I can, which is that if you are going to have sort of two vapor retarders that are significantly strong on that, like a class 1 and class 1, when the outside is less permeable than the inside, that's what really causes that problem. He does a really good job in an article, that, like I say, if anybody has questions about that, I'd love to send it to you. I think it's a great read. But he points out some ways that we've been building for a very long time that sort of violate these rules. But they've stood the test of time and sort of giving that expertise. Because I think as we super insulate structures, we use more exterior insulation. These are the questions that have been coming up for a lot of code officials, and I want to encourage people to have the resources that they need to start asking those questions and start scrutinizing, the designs that they get in and having a good basis to do it in. And sometimes that's got to come from more than the code as we look at these more robust and advanced buildings. So I'm going to wrap things up real quickly here. The Code of Honor Scholarship is open until Friday for ICC for any members that would like to try and attend. So they have $2,000 for you. Strongly recommend you throw your hat in the ring. This QR code will help get you there. And that's for more than just code officials. There are scholarships for designers. There are scholarships for a number of different roles out there. So I strongly suggest you take a look and jump on in there if you can. Would love to see you down in Florida. Colorado Code's helpline is always available for you for your help, and that QR code will get you there, or this link over here. And you'll have a survey at the end here. Let me just jump over to this, and now we'll kind of go back through the chat. And I am down to go through questions here. I see Kirk raised his hand, so let me see if I can get you on, Kirk, and let you talk. Okay, you should have permission to talk, Kirk. Go ahead.
When you were talking about the two different levels of permeability inside that last wall you just showed, did you mean the condensation level, or are you talking about the one permeable side that has the less permeability will allow water to come in? Because I think you talked about temperature coefficient, so I was trying to figure out what you meant there.
Yeah, yeah. So you're talking when I was talking about that like double vapor barrier assembly sort of issue?
Yes.
Yeah, yeah. So the way that he phrases it is that it is a function of the permeability that when the least permeable material is on the exterior, that creates circumstances oftentimes, and I think some of the assemblies he points to are like tilt-up concrete and things like that, where there's significantly more heat that's also radiating through those assemblies. He points to some instances that you'd be really familiar with, Kirk, where black fully adhered membranes on roofs used to be basically tied in our common sort of thinner commercial roof assemblies where that was your membrane on top, your roof insulation, and then an air barrier below. He was like, hey, that should technically be vapor locked. But because of the robust amount of heat that was coming through on the membrane side, that basically pushed that material, that condensation, towards the place of least permeability and allowed that system to work in some surprising ways. So I will send you the article for sure, and I see a number of other people have requested as well, so I'll be sure to throw that out there for you guys with a link, and you guys can take a look for yourself. But yeah, he points to the idea of the permeability first. The less permeable it is on the exterior, the more problematic it gets. But then it also becomes a function of temperature, like you point to.
Yeah, because there was a bunch of stuff that happened in California when they did Title 92 or whatever that was, and they were trying to make the roofs reflective. Well, that allowed the moisture to build up inside that roof assembly, and then they had collapses because it wasn't hot anymore.
Yeah, yeah, okay, yeah, that makes a lot of sense.
Thanks.
Yeah, thank you. Appreciate you attending. And yeah, I'm kind of going through the chat here. Anna Keating had a really good question at about 22 minutes in about is this significantly different for the 24 code? I would say generally no. These provisions and these definitions have really remained about the same over the lifetime of these codes, and I haven't seen any differences with that. And I do believe I think there's only a couple of minor modifications to the residential list for air sealing as well. So I don't think there's too much difference, but as we get closer to actually being able to teach on the 24 code and the state, finalizes its recommendations, because I think that'll be the trigger for us to be able to start talking about that at length. I think we'll definitely plan a class for that. And I know the roofing assemblies class I'll be giving in June should be past that point where I'll be able to spend some time on those issues. So I'll definitely give you an update as we get a little closer. And then Guadalupe, I will send you an email with a link to this manual, sir. Yeah, it's the Portland Plaster and Stucco manual. And yeah, I still have a copy at my desk somewhere, but it's a great book, and I will send it on over. And yeah, it looks like everybody else was just requesting the article, so I will take notes and make sure that everyone else can get it. If anyone else has any other, questions, comments, concerns, feel free to email me. I know we stayed a couple of minutes over. We just had a lot to get through there at the end. But I hope you guys enjoyed the class. I really enjoy talking about this stuff. This was a lot of fun for me. And I hope you guys have a great rest of your Wednesday. So, yeah, anybody has anything they'd like to follow up on, you know where to find me. Have a great day, guys. Take good care.